Okay, off we go then. So this glowing gas cloud is hot, mainly because of the ultraviolet radiation from these very, very bright, massive stars in the center of the cloud. These are very young stars, by the way. Stars form in these gas and dust clouds that we see as emission nebula, and the ones that are really bright end up making the cloud glow. The other ones are embedded within, and many of them are still forming. And you can see little lanes of dust here and things of that nature. So a lot of stuff is going on here. There's also a lot of stuff out here surrounding the cloud that you do not see. Okay, this stuff was not known until the 1960s, which is not all that long ago, about 40 to 50 years ago, because it's not visible to our eyes. It doesn't show itself off with visible light. Okay, so the Orion Nebula is just a little ionized portion of something we call a giant molecular cloud. Okay, so this is how stars are born. Stars are born in these giant molecular clouds. A giant molecular cloud is, well, it's very descriptive. It's giant, meaning it's really, really big. It's molecular, meaning it's made of gas that has collected into molecules. Now, the air you breathe on the Earth is nitrogen and oxygen, but it's not atomic nitrogen and atomic oxygen. It's N2 and O2. In other words, the oxygens have come together to make molecules. If you have hydrogen gas on the Earth, the hydrogen is not atomic. The hydrogen you would have on Earth is H2. Hydrogen likes to combine with other hydrogens to make a hydrogen molecule, an H2 molecule. And the same thing is true of the molecules in these clouds. Okay, so this is not atomic gas, it's molecular gas. And the reason for this is still somewhat uncertain, but the density of these clouds are much, much greater than the atomic hydrogen clouds that are within our galaxy. We know these things are out here now because they give off radio waves. Okay, if you could see the constellation of Orion with radio eyes, and you would have to see a very, very specific region of the millimeter wavelength part of the radio spectrum, what you would see is a lot more stuff. Okay, the Orion Nebula would be just this little bit here. Now, the Orion Nebula is like 16 light years across. It's also about 1,600 light years away, but it's very, very large. 16 light years across is pretty huge, but it's a tiny, tiny portion of this large cloud of molecules that really dominates that portion of the sky. The thing is, our eyes cannot see it. We could only see it if we could see in the millimeter range of the radio spectrum. And the reason for that is that there are mostly hydrogen molecules in this cloud. Well, the hydrogen molecules don't do much. They just sit there. But the carbon monoxide molecules, which is only a very, very tiny portion of the molecules in this cloud, well, those things are real show-offs. The carbon monoxide molecules are like little batons. Okay, they're little baton-shaped things. On one side, you have a carbon. On the other side, you have an oxygen, and it's connected with a little molecular bond. Okay, the oxygen's a little bit heavier, and the carbon is a little bit less heavy, and it spins. Okay, the carbon monoxide molecule will spin. I did mention this in class a couple weeks ago when I kind of got off on a slight tangent because of a very, very good question. But it spins like a spinning baton. But unlike a spinning baton, which you could make go fast or slow or any speed in between, a molecule, when it spins at a very, very specific energy of spin. It has basically like, quantized gears. So it has certain rates of spin that it can spin at and certain rates that it can't spin at. And it can go from a high spin to a low spin, but when it does, it jumps from a high energy spin to a low energy spin instantaneously. And as it does, as it shifts gears from a high energy spin to a low energy spin, so let's say, for example, it's going from a fast spin to a slower spin. We'll make it with smaller arrows here. So it shifts from a fast spin to a slower spin. It has to get rid of that energy some way, and it's just like in an atom when an electron goes from a high energy state to a low energy state. It gives off a photon. It gives off a photon of energy, but it doesn't give off a visible photon. It gives off a radio photon with a wavelength of 2.6 millimeters. Okay, and we see lots and lots of these radio waves that are at a wavelength of 2.6 millimeters coming from this molecular cloud in here. Okay, so the molecules of carbon monoxide, even though they're a very small portion of the molecules in this cloud, is what allows us to detect the cloud's presence. Okay, so these giant molecular clouds are mostly made of molecular hydrogen, but it's the small amount of CO that gives off most of the radio waves. And the reason that happens is because the CO molecules, the carbon monoxide molecules, emit 2.6 millimeter radio waves. They spit out these photons when the molecule shifts gears from one quantized rotation rate to another, just like we showed you up here. When it goes from fast to slow, it spits out a 2.6 millimeter radio wave, and therefore you end up detecting it. Okay, that doesn't happen with hydrogen molecules. H2 is far too symmetric to do that because you have an equal number of electrons in both hydrogen atoms. Even though it's sort of baton shaped, it's like a baton with two equal knobs on it. And because of that, even though the rates of spin are quantized, you don't have that kind of a transition from high to low. Okay, when astronomers then found these molecular clouds and figured out what they were made out of, they found that they were really, really massive. Okay, they have masses of anywhere between 100,000, a small one will have 100,000 times the mass of the sun to maybe 10 million solar masses. Okay, and again, this symbol here means the mass of the sun. Okay, this symbol here means the sun, and we're doing it in multiples of the sun's mass. Okay, they are very cold at the center of these clouds, only about 10 degrees above absolute zero. That turns out to be very, very important because if they weren't cold, they couldn't collapse into stars very easily. The hotter something is, the less it wants to collapse in on itself gravitationally. They're also very dense. Now, dense is a relative term here. Okay, dense means about 1 million particles per cubic centimeter. Okay, 1 million particles per cubic centimeter seems very, very dense to, you know, when you look at that number, 1 million particles, wow. A cubic centimeter, by the way, is again about the same size as, say, a sugar cube. So if you have 1 million particles in a sugar cube, you think, wow, that's a lot. But in fact, if you have an actual sugar cube, there's something like 10 to the 23rd particles in that sugar cube. And even if you have a sugar cube full of air, you might have 10 to the 20th or something like, you know, 10 to the 21st particles or atoms or molecules per cubic centimeter. So it's 10 trillion times less dense than the air you're breathing right now. So we call these things clouds, but they would be a perfect vacuum here on Earth. A vacuum chamber on Earth would have densities even greater than this. Okay. They're also shaded by dust. These molecular clouds have dust in them because the molecules would be broken up by starlight. Starlight tends to break apart molecules, and the stars near the cloud or in the cloud or around the cloud would break up the molecules, but there's enough dust to dim the stars. And you remember in the last mini lecture, we saw those dark cloud areas, the dark obscuration nebula that obscure starlight, and that's what helps these molecules stay intact. Okay. All right, so how does star birth happen? Okay, well, like every birth, it starts out with a good contraction. Okay, in this case, it's a gravitational contraction. The clumps of clouds don't want to collapse initially necessarily. Okay, they resist collapsing. They resist collapsing because they have thermal motions, because they're above absolute zero. In other words, they're warm. Again, warm is a relative term. Anything above absolute zero has some temperature and so has some energy of motion. And so you have thermal motions, and you also have things called turbulence. Okay, so thermal motions are caused by heat. Okay, and turbulence is similar to like wind. So there's these random motions, like you have wind on Earth, or like you have convective motions inside a cloud. If you've ever seen a time lapse of a cumulus cloud forming, that's turbulence that you see in the rising and sinking gases, things like that. So there's thermal motions and there's turbulence. The thermal motions is basically caused by temperature. Even at a very, very low temperature, like 10 degrees above absolute zero, a typical hydrogen atom will still be moving over 1,000 miles an hour. So that's pretty darn fast. It's a lot slower than it is at, say, room temperature, but it's pretty darn fast. And so you need gravity to be strong enough to overcome that motion to pull the hydrogen in. Okay. You also get that turbulence caused by heating effects of nearby stars. Okay, so the turbulence is caused just like in a similar fashion to the way turbulence in cumulus clouds occur because of daytime heating during the summer or during the spring. You would also get churning effects from the heat of nearby stars, causing there to be turbulent motions within the stars. So to collapse into a star, you need the cloud to get clumpy. Okay, that's the technical term for it anyway. You need to get it clumpy enough and dense enough so that gravity can overcome these motions. Okay, so to collapse into stars, a cloud has to be dense enough for the gravity to overcome these random motions, the motions of the temperature and the motions caused by turbulence. Okay, so both of these motions are resisting collapse. You have to have this thermal motion less than escape velocity. You have to have it less than the velocity that you would normally have to go to escape the clump. Okay. So every now and then, just by random processes, a cloud gets clumpy enough just by chance. It gets lucky. These are called Bok globules, after Bart Bok, the astronomer who discovered them. These are dense and cold enough to contract on their own. They don't need any help. They just somehow collected enough gas in a region of space because of random motions and whatnot that, oh, look, I'm clumpy enough, and it starts collapsing into the star. Most things need more than that. Most parts of a cloud need something to trigger star formation, okay? Such as colliding molecular clouds. If you have molecular clouds that are moving into one another, you can think of this as sort of like two marching bands marching through each other on a football field from one end of the field to the other, marching at each other, and then as they superimpose each other, suddenly they're twice as dense as they were before. In the case of a cloud, that means that the gravity would be greater because of the higher density, and it would start to pull material together. Okay. If you have some stars already forming nearby, the ignition of these hot stars can cause a pressure that compresses the interstellar clouds. And so new stars forming can actually cause kind of a chain reaction. It can cause pressure on the molecular cloud that can cause greater density, and therefore you end up with more star formation happening. Okay. And finally, if you have a star that already has happened, a really hot star, a really massive star, it goes out very quickly in a bang at the end of its life. These are called supernova explosions. So supernova explosions can produce these big compression waves. And basically, this is an interesting thing. This is like a phoenix rising from the ashes, so to speak, because the death of one star can trigger the formation of many, many new young stars. And that's what happens oftentimes if a supernova, which is caused by a dense hot star that doesn't last very long, if that happens near a star forming region, more star formation can occur.